Hello. So in today's lesson, we're going to look at some of the defining characteristics of polynomial functions. So if you recall in our last lesson, we kind of introduced the concept of even and odd functions and used a function's degree, whether or not it's even or odd, and its leading coefficient to determine what the end behavior was going to look like. So hopefully we have a decent handle on kind of the general shape of polynomial functions of different degrees. So in this lesson, which should be pretty quick, we're just going to delve a little bit deeper and look into some of the characteristics of polynomial functions. So first, let's look at a function with, let's say, negative leading coefficient and odd degree. So as we discussed in the last lesson, our end behavior, if it has a negative leading coefficient and an odd degree, as x goes to negative infinity, y is going to be going up to infinity, whereas as x goes to positive infinity, y is going to be going to negative infinity. So our graph could look like that. That's just an example graph. So now we want to look at some of the characteristics of this function. So as we know, the end behavior tells us that as x goes to negative infinity, y goes to infinity, and as x goes to positive infinity, y goes to negative infinity, and that you can see on this graph. But that's not the only feature of this function. So as we know, all functions have domains and ranges. So our domain consists, like the other functions we've studied, of all the possible x values. So notice that this function is going to keep going this way, and it's going to keep going this way forever. So actually, like all the functions we've studied so far, like quadratic, absolute value, and linear functions, our domain is going to be all real numbers, which we could write as any of these things. How about the range? So the range consists of all the possible y values. And you'll notice that this function, it keeps going up to infinity in this direction, and we go on our little roller coaster ride, and then it goes to negative infinity in this side. So our range is actually going to be all real numbers too. So an important shortcut is to note that all odd functions will have a domain of all real numbers. Will have a range of all real numbers, sorry. They will also have a domain of all real numbers. So we've looked at the end behavior, the domain and range, and there's a couple more just kind of characteristics I wanted to go over. So just like quadratic functions, polynomial functions have zeros, which you might see referred to as real zeros, and those is just another way of saying the x-intercepts of the function. So if we were asked what the zeros of this function were, we have 1 over here, 1 over here, 1 over here, 1 over here, and 1 over here. So these, I'll just draw an arrow to them, are real zeros or are x-intercepts. So we would have a 0 at about x is equal to negative 7.2. I'm just estimating here. 0 at about x is equal to negative 1.8. At about x is equal to 3.1. X is equal to 6. X is equal to 7.1. So you may be asked on a test problem or a homework problem to identify what the real zeros of a function are from its graph, and you just take a look at the graph and estimate. So this is 1.8, we can go in 1 and then 0.8. This one's x equals 6, so it's fairly self-explanatory how you find the real zeros of a function. Additionally, we have what we call extreme values. Extreme values is just a fancy way of saying either a maximum or a minimum. And in polynomial functions, we refer to these as local maxima and local minimums. So I'll write local up here. And the reason we use this local term is a local minimum is going to be this point right here. Because you see it's the lowest point in this part of the graph, because it's the bottom of our valley here, but it's not the lowest point in the whole graph, because this graph is going to go all the way down to negative infinity. So this local minimum, if we want to estimate the point that it's at about the point -4, -4. So a local minimum is just always going to look like the bottom of the valley, whereas a local maximum would be the top of the mountain up here. So this is a local maximum, and it's at the point at about 1 and then 3.2, for example. And again, to find the locations of these local minimums and local maximums, we just look at our axes and estimate the x and y values. So here we have another local min, and here we have another local max. And these extreme values you might also see referred to as turning points. So there's one key thing we know about turning points, which is that the maximum number of turning points in a graph, so the maximum number of turning points in a graph is the degree -1. So if we look at this graph, we'll see that it has 1, 2, 3, 4 turning points. So if this graph has 4 turning points, that would mean that it has 4 turning points, so our minimum degree is 5. So what this tells us is that by looking at this graph, we know what the minimum degree is. The degree could potentially be bigger than 5, like it could be a degree of 7 or 9, but we know that it can't be a degree of 3. Because if we had a degree of 3, then we'd have 3 minus 1, so we'd have a maximum number of 2 turning points for that graph. And this graph obviously has more than 2 turning points. So that's a way to find what the minimum degree of a polynomial function is. And I think the only thing left that I want to go over with this is that we also have, as with all our graphs, we have a y-intercept. So this would be our y-intercept, which is about y equals to 3. And like all functions, or all functions that we've studied so far, polynomial functions will have exactly one y-intercept, where they could have multiple x-intercepts. So that covers our example of a negative leading coefficient and odd degree function. Let's do another one with an even degree. So let's look at a function that, say, looks like this. So this function has a positive leading coefficient and an even degree. So our end behavior would be, as x goes to negative infinity, y goes to infinity, and as x goes to infinity, y also goes to infinity. And you can confirm that on the graph. So our domain is going to be all real numbers, because we see it goes forever in negative x and in positive x. Our range is going to be a little bit different this time. So for our range, we see that obviously this graph does not continue past this point in the y direction. So we're going to want to try to judge what the y value of this point is. So I guess this one's a little bit lower. And this looks like our lowest point on the graph, which is at about negative 3.8. So our range is going to be about negative 3.8 to infinity. And again, the range is going to be all of our possible y values. And you notice our graph is going to stretch forever going this way, but it stops here. It's impossible for us to get any of these y values, any of these outputs out of our function. So think of these like parabolas, I guess the graphs of quadratic functions, or like absolute value functions. There are certain y values that we're not going to be able to have in even degree functions. So I'll write that for even functions, our range is never all real numbers. Whereas for odd functions, the range will always be all real numbers. So this is a little bit tricky, but just by sketching a graph, it should be easy to remind yourself of what the range of even and odd polynomial functions is. So all the other characteristics of even functions, I think, are pretty similar. So we have our real zeros, or our x-intercepts, which these are right here. So we have x is equal to negative 3.8. We have x is equal to negative 1.5. We'd have x is equal to positive 1.5. And then we'd have x is equal to 4.5. These would all be our x-intercepts. Our y-intercept would be at y is equal to positive 3. And again, there's only one y-intercept, but we have multiple x-intercepts. We have local minimums over here. So these are local minimum values. And this one is at, say, 4.2 to negative 3.8, and this one is at, say, it's 1, 2, so negative 2.8 and negative 3.4. So again, we'd find those just by looking at their coordinates on the graph. And we have a local maximum that's right next to our y-intercept. So our local maximum would be the point. So we go a little bit left, so let's say like 0.2 and then 3.1 would be our only local maximum. And then we just want to look at how many turning points our graph has. So we have a turning point over here, a turning point over here, and we have a turning point over here. So we have 3 turning points. So that means that our maximum, or our minimum degree is 3 plus 1, which is equal to 4. Because I'm just reversing this phrase here. I guess let's write down an equation for it. We can have the minimum degree is equal to the number of turning points plus 1. And we could rearrange that to say the number of turning points is equal to the minimum degree minus 1. So I got that by just subtracting 1 from each side. So hopefully this little formula helps clear things up a little bit. And again, our minimum degree is 4, which makes sense because we have an even degree. But this could also be the graph for a function of degree 6, 8, 10, 12. Again, all this tells us is what the minimum degree is. So that's just a quick little lesson on some of the characteristics of polynomial functions. And in our next lesson, we're going to look into how we graph these for ourselves. So stay tuned for that.